Hello. So this will be AP Chemistry Notes, pages 75 to 77. And we start with a very simple review. If you have 0.1 molar barium chloride, no, barium hydroxide. I should actually read the problem. Barium hydroxide. What is your hydroxide concentration? Well, you just have to pay attention. Barium hydroxide gives off 2 hydroxides. So the hydroxide, whatever this is here, this has to be double that. And the barium would be the same. So in the end, it would be 0.1 molar barium ions and 0.2 molar hydroxides. Now this concept of a base giving off double the hydroxide or an acid giving off double the hydrogen or even triple the hydrogen, there's a special form of concentration that accounts for that. And you're going to think I'm making this up, but I'm not. It's really the word. It's called normality. And the symbol is a capital N. So it essentially is the same thing as molarity, but having adjusted for how many things are given off. In the case of a base, the thing is a hydroxide. In the case of an acid, the thing is an H+. Now, the number of things that are given off is referred to as the equivalence. So, something like sodium hydroxide, it only gives off 1 hydroxide, so it has an equivalence of 1. Something like hydrochloric acid only has 1 hydrogen, so it has an equivalence of 1. So it's the number of hydrogen or hydroxide that's given off. Whereas if we look at something like sulfuric acid, it'll be 2. Barium hydroxide, as mentioned earlier, will be 2. Phosphoric acid will be 3. And again, it's not how many hydrogens it has, it's how many it gives off. So be careful if you see something like these hydrogens are not given off. So don't look at those ones, it's just this one. So this would only have an equivalence of 1. And it doesn't matter whether it's strong or weak. It's just referring to can it be given off, whether it does it strongly or weakly or amazingly weakly. That is still given full credit. And as I mentioned earlier, normality is the same thing as molarity. If the equivalence is 1, they're the same thing. If the equivalence is higher than 1, it's just the molarity multiplied by the number of hydrogen or hydroxide. So take 0.1 molar phosphoric acid. It has equivalence of 3, so you multiply by 3, and it would have a normality of 0.3. And these are the same thing. Saying 0.1 molar phosphoric acid is the same thing as saying 0.3 normal phosphoric acid. And I have to be, and I grab things like acids and bases that are already put into water. I have to be careful that I read the label correctly, because in the case of something like sodium hydroxide, normality and molarity are the same. I don't have to worry about it. But in the case of something like phosphoric acid, I better read that and make sure I'm finding the correct one. Otherwise, my concentration could be off by about 3 times. All right, now the next couple lessons, the rest of this lesson and the next lesson are all going to be about titrations. No surprise, any chemistry class, well, regular chemistry class that doesn't talk about titrations is not a chemistry class. So this is a big topic, and we are going to do a lab with it. What happens is when you do a titration, basically what you're doing is you're comparing a known substance to an unknown substance. And the idea is, by comparing the unknown to something you know, you can find out stuff about the unknown. And a classic version of titration is to compare a acid or base that you don't know the concentration to the opposite acid or base that you do know the concentration. And you can figure some stuff out that way. And we'll be doing that. Now, as you react an acid and a base together, as they are being neutralized, if one hydrogen has been pulled off the acid by hydroxide, and by the way, when doing titrations, the classic type of problem is to start with an acid, and that's what you would have in your container, and then you would have your burette up here, the valve, and what would happen is you would drip in the base. So we're just going to go from that standpoint. You can do the opposite, but we're going to start with an acid, and we're going to add a base, usually from a burette. When the first hydrogen has been completely removed from the acid, that is said to be an equivalence point because you have neutralized one equivalence, like mentioned before. If the acid only has one hydrogen, it is also the endpoint of the titration because you're done. If the acid has more than one hydrogen, let's go back to this phosphoric acid here with 3 equivalents. What would happen is you would have the first equivalence point where the first hydrogen has been removed. You would then have the second equivalence where the second hydrogen has been removed. You would then have the third equivalence where the last hydrogen was removed, and that would also be the endpoint. So often you would label it first equivalence, second equivalence, and then endpoint because it's the same as the third equivalence. Okay. Now, what's been developed is an equation to help with titrations, especially if one or more of the chemicals has more than one equivalence. And you should recognize this equation looks just like MaVa equals MbVb. The problem with the equation that we've been using last year was we're assuming that everything is one equivalence. If something is more than one equivalence, we have to account for that, and that's what's happening in this new equation. Now, technically, it's supposed to be liters, so it's NaLa equals NbLb. But just like how we got a little bit more creative with the equation last year, we can do the same thing again, and this is the version I prefer you use. You can use any volume you want as long as they match, and typically everything will be in milliliters. So I've got an example here. We are going to add 0.150 molar sodium hydroxide to 25 milliliters of 0.2 molar phosphoric acid. And the question is saying, how much sodium hydroxide is it going to take? Well, since it's phosphoric acid, you take the molarity and you have to triple it to get the normality, which is here, 0.6 normality. Sometimes people say 0.6 normal. Sounds weird. There's the volume of the acid. There's the normality of the base because it's only got one hydroxide. Molarity and normality are the same. We're solving for VB, and you get 100 milliliters. The more typical question is actually not this version. The usual question, and the question that will be asked in the lab, is you'll be asked, what is the concentration of the base. And so you'll take the same equation, NaVa equals NB VB. And what'll happen is you will know the concentration of acid, and you will know how much acid you're starting with, and you will add base, keep adding base until you reach the end point, at which point you can then plug in that volume from your data. And these two things are known before you even start. That would be already determined, the normality and the volume of acid. Experimentally, you find the volume of base, and once you do that, you can then solve for the normality of the base. If it's only got one equivalence, you've also solved for molarity. If it has more than one equivalence, then you just do the necessary adjustment. Now, when making a graph of a titration, the typical graph is to put pH, this is pH over here, it got a little bit cut off right here, should be pH on the Y. And again, we're starting with an acid, we're adding a base, and so the x-axis is milliliters of base that's been added. And you can tell in this graph that we're starting with an acid because the pH starts low, and then it gradually goes up, and then ends high if you keep going past the endpoint. Let's take a look at these, and then I'll go back up to this note right here. I'm going to skip this note on C2 for now, and we'll get back to that after we analyze these graphs. What I want to first look at is the curve will look different depending on whether you had a strong acid and a strong base combo, or whether you have a strong acid, weak base, or weak acid, strong base. So first, let's just take a look at why is the pH increasing? Well, you're starting with an acid, as I mentioned. Let me get rid of some of this stuff right here. So it's going to be a low pH, not necessarily that low. This is just an example. As you add strong base, you're neutralizing the acid. So let's say we add a little bit of strong base and we go to here. In this second X, the one to the right, some of the acid has been neutralized, but we still have acid remaining, so it's still acidic. So we add more base and we get to here. Okay, now we've neutralized most of the acid, but we still have some acid, so it's still acidic. And then we get to this right here, the endpoint, and that's where the original acid has been exactly neutralized by the base that's been added, which is why now the pH is super sensitive to any tiny amount of base that's added. As far as the titration is concerned, this is over. But if you were to keep adding base, the pH would dramatically go up because you're adding hydroxide essentially to water. And then after a while, it would start to flatten out as you're just adding hydroxide to hydroxide. Now I want to take a look at these different versions. If you have a strong acid and a strong base, strong acid H+, strong base hydroxide, they are going to perfectly neutralize each other. They're going to make water. And an example here would be something like, let me go in the correct order, HCl and sodium hydroxide. That'd be the most common example there, in which case you're going to have sodium and chloride spectator ions. They're not doing anything, and they're neutral in water solutions, and you end up with a neutral end right here at a pH of 7. Now let's take a look if you have a strong acid and a weak base. So let's go HCl again, and F-, the weak base fluoride. Well, you're starting with the acid, So it's going to be a low pH. Similar situation, but this time, see what's happening. Strong acid, weak base. We have accidentally been making HF the entire time. As we add the weak base F minus to this, we have been unintentionally making this stuff, which is a weak acid. So the endpoint will not be at 7. It will be slightly acidic, and that's why this one is, in this case, I just made this up, for example, wouldn't necessarily be 5, but I just gave something that had an acidic pH. In this last example, weak acid, strong base, let's say we use the weak acid HF and strong base sodium hydroxide. We're still starting with an acid, so we're still starting with a lower pH. But then, as we neutralize it, we've got the weak acid, I'll switch colors here, HF. We're adding the strong base hydroxide. We are making water, but we're also accidentally making the conjugate weak base of HF. So in this case, when you're done, you have this leftover F minus, and this one will have basic endpoint. And again, I just made up that 9 as an example. Another thing to notice here is how big this jump is, the vertical jump. The endpoint here and here and here is halfway up the jump, and I'll get more into that in a minute why. And the jump is typically really big. So let's say here to here for a strong acid, strong base, but it's smaller when you have one weak species. And we're going to look at that in detail a little bit later on. And now I need to, let me clear this up. It's gotten a little messy. And let's take a look at this thing I mentioned here. I really wish I had more in the notes about this, but I'll just explain it now. When it says the pH equals the pKa, what it's meaning, it's the pKa of the acid. So you might be saying, pKa, what the heck's pKa? Well, it's the same thing as pH. pH is the negative log of the hydrogen ion. In other words, it's just a different way of looking at it. pKa is the negative log of the Ka. And it turns out, if you do a titration and you know where your endpoint is, let's just pick this first graph and let's just say right here. Whatever volume that took, that volume, which is, there's nothing labeled. If you go to half of that volume, so in this particular graph, halfway would be approximately right here. If you read the graph, that pH, whatever this pH is, right here, well, it'd be right here on the axis, that pH will equal the pKa of the acid that's being titrated. And that is useful because once you know pKa, you can undo the P, the negative log, and you can solve for Ka. And we will be doing that. All right, moving along. Here's a slightly more complicated titration because it's got a diprotic acid. This is just an example. It's not necessarily the graph of carbonic acid, but it would look something like this. pH starts low, and notice you get 2 jumps. You get the first jump was removed. You get a second jump where the second and final hydrogen is removed, and that could be referred to as the second equivalence point or the endpoint. And interesting to note here that I've mentioned is that whatever volume of base it took, so this would be the volume of base added, whatever volume of base it took to reach the first equivalent point. So on my x-axis, here to here, it's going to take the exact same volume of base to then go from the first equivalence to the second. And so that's why I've labeled VEQ1 equals VEQ2. So let's say it took 8.5 milliliters to get to the first equivalence point. Well, it should take an additional 8.5 to get to the second equivalence point. How big these jumps are, it depends on the particular diprotic acid. So we can't really say too much about that. So I've got some examples here and some things to go through are, what are you starting with? In other words, what's in the flask? And again, let's just do a standard titration so you can imagine an Erlenmeyer flask. That probably looks better than that, with some sort of magic chemical in there. And then we have a burette up here. The burette is a valve that we control, and it's got markings on it that tell us what the volumes are. And we're going to add drops of stuff into it. Well, the traditional is to have acid here and base here, but you don't have to do that. So let's see if we can figure it out. First one, what's being titrated? What's in the flask? Well, because the pH is starting out high, it's going to be a base. What's being added? Well, the opposite thing has to be added, an acid. So once you know one, you automatically know the other. Oh, by the way, this unit, we are only doing titrations with acid and base, but you can do titrations with other reactions. You can do other ways and other methods and other reactions. So don't be surprised when you see a problem that says a such and such titration and it's not acid base. It's still the same idea that you're comparing an unknown to a known. All right, it says label the endpoint. Well, it's right where it is in the middle of the jump. By jump, I mean like here to there's the jump. In this case, it's more of a fall than a jump. And the fact that it's right at 7 and it's such a severe jump, we can say that this base is probably strong. And to be honest, the acid is probably strong as well, based on this graph. All right, next one. Make a little more room here so we can see what's happening. What's being added? Well, we're starting low pH, so it's an acid. That means what's being titrated is an acid. What's being added is a base. Label the endpoint. It's right there, halfway up the jump. What's the pH at the endpoint? Well, I have to be honest, this graph is not great. It would really be nice if we had grid lines to help us go through it. But if you just kind of estimate, it's kind of about here, right about 5.5, give or take. So I just said 5.5. And now I want to look at this pKa thing. So again, when I say what's the pKa, I'm asking the pKa of the acid in the titration. What you do is you see what is your volume at at the endpoint, which is 25 milliliters. You then go to half of that. Now, again, this graph doesn't have everything labeled, so if it was labeled, we would go to 12.5, but since it's not labeled, I just kind of estimated that it's right about there. And then you just read the pH. The pH right there, I said, is right about 0.5. Actually, it looks like it might be a little bit higher than 0.5, but I did 0.5. If I then ask for the Ka, you would just undo it like we normally undo like a pH when you go to H+. You would say that Ka is 10 to the negative pKa, and so on. And that should work out here. And another one for practice. What's being added? Well, low pH, acid. I said it again. I keep doing that backwards. What's being titrated? An acid, low pH. What's being added? A base. Label the equivalence points. First jump, second jump. This one's kind of interesting that the first jump's small and the second jump's big. That's unusual. Typically, you see the opposite. You might see a big first jump and a small second jump, but okay, let's just go with it. If I asked for the endpoint, I didn't, but you would say that this is the endpoint as well, but I didn't ask. What's the volume at the first equivalence point? Well, 25. Second, 50. That makes sense that they were equal amounts to get from the 0 to the first and from the first to the second. pKa1 is referring to halfway to the first equivalence point, and I estimate that to be a pH of about 1.1. Over here, this would be pH here. And the second, pKa2, what you do is you go halfway to the second equivalence point. So right here, that is halfway, I should say, between first and second equivalence point. And again, I just did a very rough estimate of 1, 2, 3, 4.1, right about there. And we could take this and we could solve for Ka1 and we could solve for Ka2, but I don't bother with that on this one. All right, now we need to talk about indicators. So when you do a titration, you need, let me go back here actually, you need to know when you reach this magic spot right here, when you reach the equivalence point or endpoint. You need some sort of indication. And the most traditional way is to use an acid-base indicator, which will change color. And that's what we're going to look at right now, is how those work and how to choose the right one. So what happens is the indicators you can think of as a weak acid, which we'll abbreviate HIN, H for the proton, IN for the rest of the molecule. They have two versions. They've got the version that the hydrogen is stuck to, which is called protonated. They've got the version where the hydrogen has been taken off, which is called deprotonated. And the reason they work is because they have different colors. So HIN, protonated, is a different color than IN minus. So let's take one that you should have seen before. You would have seen this last year. You'll see it again this year. Phenolphthalein, which is a very odd word. It is pink when it's in a base, and it's clear when it's in an acid. Now, the reason it changes like this is because it undergoes an equilibrium shift, like I mentioned here. And that's what forces it to change color. So which is the peak substance and which is clear? In other words, I want to know which of these, HIN and IN minus, is pink and which is clear. Well, it says pink is when it's in a base. Well, if it's in a base, it is going to pull the H plus off, and the amount of H plus is going to go down. That will shift equilibrium to the right, and it will be the deprotonated version. It's clear in an acid. Well, of course, in an acid, you've got a lot of H plus. That's what acids do. If you've got a lot of H plus, the H plus will go up. That will push equilibrium to the left, and that means it's the acid version. So when the phenolphthalein indicator is in acids, it's pushed left, and that one's clear. And when it's in bases, it's pushed right, and that is when it is pink. And the same thing happens with all the acid-base indicators, of which there are many. This chart is in your packet of worksheets, right around where we are. It's not in your lecture notes. I don't want to change that. I want to do that. There we go. And this is just a partial chart. There are many. I start with one that has a fairly large Ka, and then it just gradually goes through smaller and smaller Kas until you get to this one. They seem to often have really cool names. Oh, I didn't mean to do that. Let's go back there. Like Titan Yellow and alizarin, or however you pronounce that. So yeah, I like their names. Really wants me to move that page around, but I'm not going to do it. Okay. Other interesting things on here to note is you'll see all of them are only on here once, except thiamol blue. I guess I'll use a blue pen. Thiamol blue is there twice. What that means is that it must be diprotic. It must be H2 something something. And so when it says first hydrogen, that is when it has lost that first hydrogen. And when it says second, that's when it's lost its second. And note the Ka is smaller for the second, of course. There are some acid-base indicators that actually have more than 2 protons to lose, but they're pretty rare. Or they might have a additional version where instead of losing a proton, they gain a hydroxide, and so on. Don't worry about this yet. We've almost gotten to that, but we're not there. So let's go back to the notes over here. Number 2. Most indicators are complex molecules. They themselves are weak acids with a Ka that we just saw. And so you can write a equilibrium reaction or equation. You can then write a Ka expression for them. And again, I'm just abbreviating the complex part as IN. The color change happens when the 2 versions are roughly equal. So when one of them dominates, it's just going to be that color. But when they become equal is when you start to see the switch from one color to another. So if we assume that they're exactly equal, we can cross out HIN and IN minus since they're equal. That now gives us this equation. Ka is equal to H plus. If you take the negative log of both sides, you get pH from, let me switch colors here. Negative log of H plus gives me pH, and the negative log of Ka gives me pKa. Now I want to clear up some confusion that might happen. You might see this right here and say, wait a second, pH equals pKa. But didn't we see that earlier when we were talking about this thing up here where I said that it's at the halfway point? This is regarding the pKa of the acid that's being titrated when I was talking about the halfway point. Down here, I'm not talking about the Ka of the acid that's being titrated. I'm talking about the Ka of the indicator, which is a different thing. So be careful. This statement here, that pH equals pKa, this is useful for helping us find the appropriate indicator. I could see how that could get a little confusing, and we'll talk about it in class too to clear this up. So what you do is you figure out what pH do you expect your titration to end at. You need an indicator that has a pKa that is roughly near that pH. So again, I'm talking about the Ka of the indicator, not the acid that's in the titration. And so you pick an indicator who's got a Ka near that pH. And number 6 just says you have a little room for error of about 1, plus or minus a pH or pKa of 1. Going much beyond that, you might introduce air into your lab. So let's go through an example here and we'll go back to the chart. Let's say we're going to titrate weak acid with a strong base. What that means is that we will accidentally be making a weak base, like the graphs we looked at earlier. That means our endpoint is not going to be at 7. It's going to be slightly basic. So of the options I gave here, 5 or 7 or 9, the best choice is 9. It is determined that the endpoint will be, and I just made this up for this example. So this 8.8, I just came up with that just so we would have something to work with. So let's say we are doing a titration and we know that the endpoint should be at 8.8. I'm asking what indicator would be the best one based on the chart I gave. Well, what we need to do is we need to find an indicator that has a pKa that is as close to 8.8 as possible. Now, if we go to the chart over here, the one that keeps trying to change size on me, these are all Ka values. So it's easiest turn them into pKa. So if I take the negative log of this one, I got 7.6. The next one, 8.4. The next one, 9.6. And the next one, 10.5. And so they're all in the discussion. But we said that the pH at the end point was 8.8. And you want to stay within that and be as close as possible. So 7.6, that's pushing it. That's a little more than a value of 1, so that's not so good. 8.4 is okay. 9.6 is okay. 10.5, no, that's too far away. And even though 8.4 and 9.6 would both work, the 8.4 is closer to 8.8. So in the end, this one would be the better of the two. So phenol red, if we had that choice, would be the better option. And I believe I also have this over here. Yeah, I have the same idea listed here. I didn't even bother putting, what was it, phenolphthalein? That was the 4th one. Yeah, I didn't even bother doing that over here. And notice the way I solved that was I compared pH at endpoint to pKa of indicator. You could, if you want, get rid of the P's and do H plus at endpoint to the Ka of the indicator. But at this point, you'll be looking at exponents. It's not quite as obvious, but that will work as well. I have a note that if you do a strong acid and a strong base titration, the jump is so huge that just about any indicator anywhere near the endpoint will work. That is true, but you still want to get as close as possible. So if you know that it's a strong acid and a strong base, and you know that it's going to be near a neutral pH, if you had a choice, something right about here and here would be decent options. Using phenolphthalein way down here, it works, but it's not necessarily the best choice. So sometimes you just do it based on what you have available. And that should do it. We'll be doing a lab with titrations and a few different homeworks. And that takes care of this section of notes.